Okay, so given a histogram, remember that as we looked at this single variable, whatever the variable may have been, each bar represented some frequency or even relative frequency, where relative frequency can be thought of in percent terms. This is important because as we're analyzing the shape of graphs such as a histogram, we like to be able to think about a smooth curve passing over this histogram. And we get especially happy when this smooth curve happens to be exactly bell-shaped or normal, or at least approximately so. Because what we start to do is we start to say, okay, I can look at the concept of percent under this bell curve without the bars. Remember, with the bars, we could have said, for example, hey, look, that little bar right there that I had just shaded, that can represent a percent, right? I can calculate exact percents in my exact data. But instead, we like to move beyond that. We like to move in a direction of saying, yes, my original variable met the proper shape, and because of that, I can now look at the general balance that all bell-shaped curves will have as long as I know their mean and standard deviation. And as I look at that, I can consider the area under this curve to represent the percent, very similarly to the percent when I was looking at original data, but the percent in theory of any data for this particular variable. So it's like we're going up a notch with what we're thinking about. And again, we're thinking about mu in the center. That's the measure of center that we choose to use with histograms and with bell curves. And we use sigma. Remember, sigma is that average standard distance from the center as our step size. And then we start to say, okay, well, if we do in fact qualify with the prerequisite of having something bell-shaped, we have something called an empirical rule. So again, the prerequisite to talk about the empirical rule is we must have a bell-shaped distribution. And if we do qualify as having something bell-shaped, we can start to at least think about the percentages under these curves in a very formalized, consistent manner, even without technology. Now, technology is more accurate. However, the empirical rule gives us some rules of thumb that we can use. If we know the center and we know the standard deviation, we can use with just in our minds. We can figure and calculate these things. So the first thing is taking the center and using the step size of that standard average distance from the center. We can say, you know what, plus or minus one step from the center. See the two little tally marks I've made above and below mu? Plus or minus one standard deviation. I know that if I have the properties I'm looking at on this picture, if I have this shape that I'm demonstrating, that I should have approximately 68% of that variable, whatever it was, present. So for example, if the variable is female heights, 68% of all female heights will be between approximately this value and this value, whatever the standard deviation gives us, or it added and subtracted to the mu would give us. And then still building from the center, we can go out even more. We can say, you know, let's look at 2 steps above and 2 steps below the center, that mu, using again this step size that's specific to this data. So going above 2 steps, below 2 steps, the empirical rule tells us we have approximately 95% of that variable present within plus or minus 2 standard deviations. And then if we go one more step out, we can say, okay, well, now I've got 99.7% of my data. Now notice you don't get 100% even with 3 step sizes out. Notice that I just now extended the legs or the edges of that bell curve to remind you, or to let you know if you didn't know, that a bell curve is considered to go forever on both sides. So we never would say I have 100%. We would always leave a little bit off, just like in this picture where we're saying that we have the bell curve with 99.7 between plus or minus 3. Now also, in addition to those, we have the idea of symmetry that helps us. So symmetry can be used to divide this thing. So notice, like for example, if I cared about the left hand side, I could say, you know what, I know for a fact there's 50%, because a bell curve does have 100% under the entire curve, there's 50% on the left hand side of mu. So using that symmetry can be used with any little wedges I care about on the picture. Now, sometimes it's more valuable to use something called a z-score. You know, because for instance, if this had been women's heights and we had some kind of average of 60 inches and a standard deviation of you know, plus or minus 2 inches on average from that 60 for women, we might say, you know what, that's fine and dandy, and yes, I could calculate, you know, 60 plus 2, 60 subtract 2 for 68%, but maybe I want to standardize this. Maybe I want to compare women to women, and then I want a graph of guys, and I want their average height and their standard deviation. And with knowing those numbers would be different, it would be certainly easier if I could standardize these things, women to women, apples to apples, men to men, oranges to oranges, right? Because the idea would be, keeping similar to similar, I can put them in the same type of language. So notice from the z-score that we have x, that's the variable for whatever the number is in that column that I want to convert on the z-score, subtract the average divided by the standard deviation. And so what cranking our values through this formula will do for us is it gives us this z distribution that always has a center of 0 and always has a standard deviation of 1. So for instance, you can easier discuss things like that center 68%, because that would just be -1 and 1, since the standard deviation is exactly 1. And then of course for 95%, between -2 and +2 for my z-scores, that would be my 95%. So basically the way this plays with the original picture that you just saw is the exact same. The same balance of the data, the same interpretation of the data. It's just the z-score does put things on a similar playing ground so that you can discuss different items together a little bit easier. So now moving on to the idea of a box plot. This is another way of looking at the balance of data. And you know, we often do still, for unimodal data, we do still try to focus a lot on the center of the data and what is typical. For a box plot, though, we take a different approach. Rather than looking at mu and the standard deviation like you saw above, we end up looking and saying, you know what, I care more now about things relative to that median, that other measure of center. Because the median is a good way of getting to center, especially if I have some sort of outliers to get to the center without as much interference from every single individual data. So let's look at the box plot conceptually. Let's say arbitrarily we have 8 data points, or 8 values, and we have listed these values in order. Now the reason I'm using the literal dots on the screen here is because I don't want us to get too attached to specific numbers or how close or far they are from each other. We could have an outliers in this. We could have data that's all the same number. We could have any kind of balance. For example, these two on the left, they could be outliers, right? They could be the same value. The biggest thing is these values are in order. I'm pretending here like I've listed them from the lowest value to the highest value, because you all remember how to find just a basic median. You do need to have your values in order so that you can find the literal center. So looking at whatever data points or values we had, the idea of a box plot first is we literally cut our data into half, right? That's the median, that first line. So 1/2 of the data here on the left, 1/2 of the data here on the right. And here, you know, we're saying sample size is equal to 8, so, you know, there's literally 4 numbers on the left, 4 numbers on the right. If you want to think about it as like in the left-hand box versus the right-hand box. And then it doesn't matter the spacing of the numbers. I want to keep saying that over and over. As far as how many numbers go in each section, what percent in each section of a box plot, no preference is given based on where the numbers are located. Right now we're just throwing them into a box, then adding lower median, which is called Q1, upper median, which is called Q3. So notice I took that lower half and cut it in half, and the upper half and cut it in half. Now we have quartiles. We have 1/4 of the data, 1/4, 1/4, 1/4. Again, all this means so far is the same number of numbers in each box. For 8 numbers, I have 2 in each box, 2 in each section. No matter what those numbers were, I just threw the lowest 2 in one box, next 2, next 2, next 2. Remembering also that quartiles, just like a quarter is 25 cents out of 100 cents, a dollar, a quartile is 25% out of 100%. So 1/4 is the same as 25%. So usually rather than 1/4, 1/4, 1/4, you will notice people say 25% in this section, 25% in this section. And here's the labels again. Q1 is that lower median. Q2 is the exact center median. Q3 is the upper median. And by lower and upper median, I'm saying you took the half and you halved it again on the lower side and on the upper side. And 25% in each of those regions. 25% of the data. Okay, so there's also the idea of percentiles. So these words ILES, when you see that at the very end of these words, like quartile, percentile, technically that actually means cumulative area to the left, or cumulative percent, excuse me, to the left. So 50th percentile would be 2 of the 25% blocks. The 25th percentile would have just been the first lowest block up to Q1. So in case you ever come across someone talking about percentiles, that's the most common language you would hear in this kind of context of thinking cumulatively. They're just saying that whatever percent happened equal to or less than whatever the heck they're referring to. So again, on these box plots, you can go into that kind of notion of percentiles and things like that. That's not usually where we spend a lot of time, though. We really spend a lot of time, notice up here on this box plot where I just shaded some green, we spend time focusing on what is typical, on the center region of our data when we have unimodal data. So notice here on this box plot, on this separation of the data, we will be focusing a lot on the center. Right? The center, let's see, 25%, 25%, the center 50%. So up top we had center 60% for plus or minus 1 standard, or 68, excuse me, percent for plus or minus that 1 standard deviation. Down here we have the center 50% around that median whenever we're looking at what might be typical for our data and we're trying to understand. So this center 50% is it's the points that fall in between Q3 and Q1, right? And so actually this range, the distance between these upper and lower medians is called the IQR, the interquartile range. And this is calculated taking Q3, whatever number that is, subtract Q1, whatever number that is. And so the distance between those gives us some understanding of the spread of the data in the center of our data set. How far apart is that 50% in the center of our data is what the IQR is telling us. So here I want you to look, I've drawn a number line. Because the idea is that once these values have been put into the proper bin or section of the box plot, we actually take this idea of sorting out our data like this, and we stretch the information across a number line now to begin showing some scale to these values. So notice I'm putting Q1, Q2, Q3, right? I'm putting markers there for those division points. This is the center 50% of my data. And I've deliberately drawn it just a little bit not perfectly symmetric because, again, if we had a number line, you don't draw the box plot literally on the number line. It's above the number line, but you're taking those data points and you are stretching them, still keeping them divided like we've discussed across this number line. So still in that lower box right there, you still have 1/4 or 50% or 40, excuse me, 1/4 or 25%. The upper box 1/4 or 25%. And then what we also do is we say, okay, well actually I didn't show you on the separation down here for the data, but we actually also have the maximum as the highest value and the minimum as the lowest. So I'm adding those now, and so the idea is we would have these these whiskers is what we tend to call them, right? That extend out to the max and the min. Now, this is the most basic version of a box plot, where the whiskers on this box plot or box and whisker plot, they extend to the minimum, to the maximum, and you have that cat nose is what I like to call it, right in the center, showing that IQR, that center 50%, that spread of the data. So still 50% in the center, right? But of course, if we take that spread, that distance like it's a ruler in the 50%, and we took it and added 1.5 times that spacing above Q3, and then we did the same thing below Q1, take the spread, the distance of that little cat nose right there, right, and take it to the bottom to Q1 and subtract 1.5 times that actually does give us a measurement tool for outliers. So some versions of box plots will put a star on the graph. Let's pretend this over here was an outlier. I know it's not to scale at all, but a star on the graph or even a dot to represent, hey, yes, we had this value, but it's not typical. It's too far away. It's not, it's beyond even 1.5 of the spread of that center 50%. So it's just really not typical. And then we'll take that whisker and we'll extend it to the next value that's not considered an outlier. So again, outlier, 1.5% times the IQR, added above the Q3 or subtracted below the Q1. To figure out, when something is just too far away to consider it typical. And then up here, look back up here at this Z distribution for just a moment and the other bell curve. Beyond 95%, we would say that means beyond the center 95% would be, let's see, on the Z distribution, lower than -2 or higher than +2, right? For a Z score, once it's been normalized. That would be an outlier. Or lower than -3. Or higher than +3. I mean, remember, -3, +3 correspond to 99.7%. So beyond that, we also have outliers up here on these pictures. And looking at original data, you would just count out those steps. If we did have that 60, we would say, okay, we'll subtract 2 a couple of times, twice, right? So we're looking at, let's say, 60 subtract 2, that's 58. Subtract 2 more, that's 56. So anything lower than 56 on the upper picture would be considered an outlier. An unusual number. And then, of course, take away 2 again and get to that 54, and now you're very unusual if you're below 54 inches. And same idea for the upper side. Now down here on the left, you see I just now kind of sketched a picture of a box plot that could be more kind of stretched out, right? Because the idea is you are taking the separated data and you are stretching it across the number line appropriate to where the numbers actually would fall, right? So the reason that this is useful is because if you look here at this cat nose, look at how it's kind of chunked together, how it's smashed. It's not symmetric, it's smashed on the left-hand side. And then the cat nose is kind of bigger and more spread out on the right-hand side. This shows us how the data is clustered, right? So we have kind of more spread on the right-hand side. And then on the left-hand side, because that cat nose is kind of smashed together like that, and even that whisker tends to be smashed usually when this is happening, that shows us that there's dense data. A lot of data is clustering together. So if we compared a box plot like this, if our data was unimodal, a box plot like this, it would compare to a smooth curve that looks like this down here, that would be skewed right, or positively skewed, where outliers are on the right-hand side, and most of my data is right there under that mode, and the mode is where the cat nose is most clustered up. The mode, the most popular height and frequency, is there on the left-hand side, where we see that bump. So again, box plots are just great for looking at the balance of data, just like the bell curves were, with the mu and the standard deviation.